Hello everyone, thanks for joining today's colloquium seminar. Today we have Dr. Sercan Aygun as our speaker. Dr. Aygun received his bachelor's degree in electrical and electronics engineering and a double major in computer engineering from Osman Gazi University, Turkey in 2013. He completed his MS degree in electronics engineering from Istanbul Technical University in 2015 and a second master degree in computer engineering from Anadolu University in 2016. Dr. Aygun received his PhD in electronics engineering from Istanbul Technical University in 2022. His PhD work has appeared in several PhD forums of top conferences such as DAC, ICCAT, and ESP. He received the Best Scientific Research Award of the ACM Student Research Competition SRC in 2022. He is currently a postdoctoral researcher at CIMIX University of Louisiana. He works on emerging computing technologies, including the stochastic computing and machine learning. With this short introduction, we are all ready for today's session.
Thank you very much, Dr. Najafi. Thank you very much for your introduction. Hello, everyone. My name is Sercan, as Dr. Najafi introduced. Today, I'm going to talk about stochastic bitstream-based vision and learning machines. Mostly, I will be presenting you the background and the simulation side, but in the second half, I will be giving some vision and machine learning application addressing the binarized neural networks. The outline is first background to tell you the emerging computing methodology. Stochastic computing is one example from the unconventional computing methodologies. There will be three main subsections: the Agile simulation, hardware-inspired image processing, and the learning machines for some neural network applications. And then I will conclude my presentation. Stochastic computing, abbreviated as SC, dates back to 1960s, has regained the attention in the last decade, especially with the improvement of neural network systems. Researchers try to find efficient hardware platforms. And since stochastic computing brings hardware efficient solutions, researchers start to use this hardware efficient platform for some vision and machine learning applications. There are some advantages to use this emerging computing paradigm. For example, the fault robustness is the first and the most important thing, since we represent the data in an unconventional way. We use the bit streams, different from the base 2 format. I will be introducing with an example to produce a bit stream. For instance, we have a scalar value 4, and we need to encode this scalar value into a bit stream. Let's first remind the base 2 format, the conventional digital representation in our memory. So we normally give bit significance to each bit, like a 2 over 0, 2 over 1, 2 over 2. So each bit has a meaning for us. And then we multiply with this binary values, zeros and ones, to represent the scalar value. However, we assign, like from right to left, least and the most significant bits to our representation. And what if we have a problem in memory, such as the bit flips? In stochastic computing, we handle this encoding procedure by using the cumulative count of the logic ones throughout a bit stream. And these binary zeros and ones occur randomly. So the position of any 0 or 1 is not important. Here is an example for scalar 4. We have 4 ones throughout a bit stream, the size of 8. But there are multiple possibilities because it's just random. The most important thing is the total counts of the ones throughout the bit stream size of n. Here we need to define the probability also. We may say that if we have a scalar 4, if we have the bit stream size 8, 4 over 8 as a probability of getting ones throughout the bit stream. Here there is no bit significance, so even if you have any problem at any position, you will be having an advantageous position with respect to the base 2 representation. For instance, from the right to third position, we have a bit flip. Bit flip is if you have a 1, you will have a mistakenly 0. If you have 0, you will have a mistakenly 1. So for this flipping in base 2 format, you may lose the information. Even though you are presenting 4, you may have 0. But in stochastic bitstream representation, it just affects you plus minus 1 as an error. So when we have flipped this third bit position in base 2 and the SC format, instead of 4, we have 0 in the base 2 format, but we just have 5 instead of 4 in the SC representation. Fault robustness is the first thing that we can list as an advantage. And also we need to mention about the low hardware cost. Roughly speaking, we have multiplication with just a single AND gate. I will show you an example to prove how we do it. Also, there is the massive parallelism because you use less hardware units like AND gate for a multiplier. Scalability and progressive precision, but these are not the scope of this presentation. And also we have some weaknesses because we need to represent long bit streams to represent your scalar value. It based on your scalar value range. You may have n bit stream size equal to 1K, 10K. And also you need to generate the bit streams by using some special modules in your hardware, or even in your software. So the bit stream generation cost is another weaknesses of this computing approach. We have also the approximate results, but in some papers, you may see that they are exploiting this approximateness as an advantage. And also we have the energy issues. Again, it's not the scope of this presentation. Let me first introduce you how we generate the bit streams. We need to generate a random bit stream. We need a random source. We have two basic steps for this. We generate a random number and we compare our scalar value with that random number. We have n cycle. Here I just show it as a loop. And here there's a pseudocode. From first to the nth position of your bit stream, at each step, you independently generate a random number and you compare this random number with your scalar value x. If your scalar value is smaller or equal to your random number, your related bit position is 0. If your scalar value is greater than the random number at each iteration independently generated, then your related bit position on the bit stream is 1. So based on this, you roughly generate your bit stream. But it doesn't always guarantee that you perfectly have 4 ones for the 4 scalar example, because there is a random fluctuation error. So we need to keep in mind this because this is the well-known problem in stochastic computing systems. From the hardware perspective, we have the linear feedback shift registers as a hardware module used in a real system. This is a random number generator. In a binary format, it gives you a random number to be compared with the scalar value for bit stream generation. This is a 3-bit example of an LFSR. You have an initial seed to trigger your LFSR. For example, here it's 001. And you have tap points that you take the feedback, you XOR it, and then you shift and rotate your values at each cycle. As you may guess, it always has a cycle, and at each cycle you will have the same list. So this is the reason why it's called a pseudo-random. Okay, somehow it's random in hardware, but we call it the pseudo-random. And when you generate these binary numbers by seeding your initial value, at each step you compare your scalar and decide whether you are as a scalar greater or not greater. You just set or not set your bit position. This is a one way from the hardware perspective to generate a bit stream. Also, very importantly, we have another bit stream generator for stochastic computing using the Sobol-Loeb discrepancy sequences. You may just pay attention to the plots on the right-hand side. You may see the random case and the Sobol case. Here it's pseudo-random, is just random, but Sobol case is a little more structured. Even though we are dealing with stochasticity, the probabilities, we may have some structured pre-recorded values, and we may use them because somehow at a position, we will need a uncorrelated bit streams. Sobol sequences, it's just, let's say, it has a math, but I will not give any information today. Let's assume that it's just a pre-recorded values in between 0 and 1. You just read them from MATLAB's build and Sobol set generator, and you just compare your scalar value. Here I show 2 examples from the first and the second Sobol values from the MATLAB's build and Sobol generator. And you may just compare your values, your scalar value from these Sobol sequences. First and the second Sobol sequences, for instance, has a good property if you compare the generated bit stream from the first and the second Sobol sequences in terms of the correlation, which will be important for us. This is the reason why this property is important. To deal with the positive and 0 is not a big problem, but we need also implement some negative numbers. For unipolar representation, we are good for positive and 0. But if we need some negative numbers, we need to use the bipolar encoding. Here I show x over n as normalized by your scalar value normalized by n. So your maximum representable value is n. So your normalized values is between 0, 1 or -1, 1 if you are dealing with the negative numbers and you are using the bipolar encoding. So we have full of zeros for 0, full of ones for 1 in unipolar representation. And in the bipolar representation, we have full of zeros for -1 and full of ones for 1 representation as x, x is equal to n. So can you guess how we can embed, encode the information of 0 for bipolar encoding? What is the probability value that we have throughout this bit stream if we are embedding x is equal to 0? Do you have any guess? It's just half of the bit stream elements with ones, half of them with zeros. But here I just show it as if it's a unary bit stream, like first ones and then zeros. But no, it doesn't have to be like this. Your ones and zeros are just random. Your cumulative total ones are important. This is just for illustration. But the most important thing here, you have an exact middle position for 0. You have equal zeros and ones in your bit stream. This is very important, the contribution that we propose for the binarized neural networks, because we use a sign function and we need to, based on majorities and minorities, we need to decide the triggering or not triggering a neuron. So here, using the bipolar representation, we decide this by looking at the majority of the ones for the positive numbers and minority of the ones for the negative numbers. After the data representation, we need to look at some arithmetic operations. We have 2 very important from the math, like multiply and accumulate. I will first represent the multiplication. If you are using unipolar representation, you need to use for multiplication the AND operation, AND logic operation. And if you are dealing with the bipolar encoding, you need to use the XNOR. This F I will be using today as a stochastic output function. So which means that you have some input probabilities. After you bit by bit process your input bit streams, you have output bit stream at the output of your logic gate. It has another probability shown here as py, and this py has a function, and we call this stochastic output function. If we have good correlation, I will explain the details. We have the multiplication for AND and XNOR when we use the unipolar and the bipolar representations. So let me give you an example for unipolar representation. Let's we have x1 is equal to 4 and x2 is equal to 6, and we have n bit stream size is 8. In terms of probabilities, we need to stochastic output function as py is equal to px1 multiplied by px2. So our probabilities is 4 over 8 and 6 over 8 in terms of getting ones, and the expected value is 3 over 8 after the logic processing of the bit streams at the output of the logic operation. Here, I first show you an example. I have 4 over 8 and 6 over 8, and I just randomly generated these bit streams, but they are fully aligned on the left-hand side. And I have 4 over 8 at the output. I was expecting 3 over 8, but I am getting 4 over 8. So there is a, let's say, problem because it's not the expected value. And also, I have another example. ones, the overlapping of the ones here is at the maximum position. If I make them far from each other, I am just, for example, making the second operand to the right aligned. So the 1 and 1 from the first and second operands is minimally aligned this time. And I have the 2/8. So my expected value 3/8 must be something in the middle. So when I just again randomly generate 4/8 and 6/8 with another distribution, I have correctly the 3/8. So we call these three representations actually the maximally correlated bit streams, minimally correlated bit streams, and uncorrelated bit streams. And if we look at the output functions, the expected one for uncorrelated is the multiplication. So here we need an uncorrelated bit streams if we are using AND or XNOR in our unipolar or bipolar representation. The bit streams for the first and the second operand must be uncorrelated. This is the reason why I mentioned you for the Sobol sequences has this great property. If you use the first and second Sobol sequences, these two bit stream representations of first and the second operand are already kind of uncorrelated with each other. But in random case, you may have anything in between minimum and maximum. So it may not give you the perfect multiplication result. So let's look after this correlation information. We will be using this. Let's look at the agile simulation of it, because even though you make a software simulation, you may need the long bit streams like 1K. I told you in some applications in the literature, there are 1Ks, 2Ks, more than this. And imagine you have cascade systems such as some layers and neurons in your neural network simulation. You may need to generate and process bit by bit by using MATLAB, this bitwise operators, your bit streams. It takes memory and it takes time. So to reduce these two parameters, we just propose a new approach to process the bit streams without generating them. I'm always keeping the same 4 and 6 example, and we have 4 and 6 as the scalar values. And I just randomly generate 4/8 and 6/8 related probabilities bit streams. I colored them based on each position that they have. So we have 2 inputs. And from these 2 input bit streams, if we look at the overlaps, we have 4 possible couples: 0, 0, 0, 1, 1, 0, and 1, 1. I am calling this overlap bit stream. And based on each overlap, I just give them some letters. If we have 0, 0, I just represent it with D. If we have 1, 1, I represent it A. If we have 0, 1, it's C. And if we have 1, 0, it's B. I am trying to actually not to generate the bit streams, but to generate the counts of these ABCDs. And I will call this the contingency table. You may set an analogy between confusion matrix and contingency table. We are not dealing with the outputs, but we are dealing with the inputs. So here it shows for 4 cells at each of A, B, C, and D, we hold the cumulative values of A, B, C, D for these overlaps from the bit streams. Actually, our main motivation is not to process bit by bit bit streams, just to process directly the scalar values to obtain the output value of the logic operation. So I am trying to use only the scalars to generate this contingency table, abbreviate the CT. Here at that point, I need to represent you a formal definition of correlation. In the literature, it's just years ago, they proposed a SCC, stochastic cross correlation metric. And here these ABCDs are just the ABCDs that we use. And it's a piecewise function, but if you look at the numerator, it's AD minus BC in both sides. So this is important because I will be using it for optimization. This SCC function, based on the correlation of 2 input bit streams and their relation A, B, C, D relations, their cumulative values, this SCC functions, when you run it based on these values, it gives you an output showing the correlation between these 2 input bit streams. If it is giving you the 1, it means they are maximally correlated. And if it is -1, if SCC metric value is -1, your bit streams are minimally correlated. And there is one more 0 correlated calculation, and I will return back to here, but let's first look the maximum and the minimum correlation. You may remember from the previous slide this example for the maximum and the minimum correlation. the maximally aligning the ones, 1 and 1 position overlappings, and then minimally aligning them. I just need to here mention about the 1, 1 is a special case. It's abbreviated as A in my table. Actually, it's an AND operation. So A is a prior CT primitive, and it's always a reference. So we will always use to find the value of A. I will tell you why. For this minimum, maximum and the minimum correlation case, I have a minimum function as an output function. So imagine if you have a maximum correlation, you may use your AND operator as a minimum selector, by the way. So we have this function as an output, or we have this kind of adder. This is called the saturated adder function at your output. By using these formulas, I may set A max and A min, which means that if you are having the maximum, maximally correlated bit streams, like here, you have maximum numbers of A's, like here there are 4, and here we have 2. You may set A max and A min by using the formula that we have. And it's just the same formula, but I am not dealing with the probability values. I am dealing with the scalar values, x1, x2, n. N is the bit stream size. So I am just using this formula to initially set A. So I have a CT table, and I first decide the A to set my table. Here, I need to find, after A, I need to find B, C, and D. Actually, if we mention about the x1 and x2 first and the second operand bit streams, the decisions of the total numbers of ones in an x1, it's based on A and B, because A is 1, 1, B is 1, 0, and X only having ones from A and B, because C is 0, 1, and D is 0, 0. So your first operand is related to A and B, and your second operand, the downside, is only the ones coming from the A and C. So to decide B and C, which means X is equal to A plus B, X1 is equal to A plus B, X2 is equal to A plus C. So you may have your B and C values from this equity. And when you decide A, B, and C, because your A plus B plus C plus D, so all elements is equal to N, you just decide your N subtracting A, B, C from the N. So by that way, you may set a CT table by setting your A initial value to maximum or minimum, and then you set your table based on the maximum or minimum correlation. Here, there are some steps that I told you, like if you correlate maximally and you set A, you guarantee that B and C is minimum and D is maximum. And I just apply these two branches for the positively and negatively correlated, which means maximally and minimally correlated bit streams. However, as you may remember, if I need to play with multiplication for AND gate, for example, uncorrelation is very important. And I also need to decide exact middle point for the 0 correlation, maximum and minimum based on the formulas, and it's easy. And I need to find the proper formula for A0. So I need to initially trigger my CT table with A and with A0. Thereby, I will decide B, C, D. And all these representations will be representing 2 bit streams having the 0 correlation. And again, I call this example. So I will be trying to implement this multiplication operation. So this is the reason why I need the uncorrelation, 0 correlation. The first come to the mind is the heuristic solution, just taking the average of A max and A min. It's working, but it's not perfectly working. The first I tried is just taking the average of maximum and minimum A values and having the mid A mid, assigning A as A mid, and then decision of B, C, D. And then I make some logic operations, I will tell, giving some results, but not perfectly. As a second solution, actually, we have a third solution for polynomial fitting, but I will not mention it today. We have the SCC optimization. So I mentioned you that the numerator of SCC function having the same AD minus BC. So if you make it equal to 0, your function will be 0. If your function is 0, your correlation is 0. So if you optimize it and if you try to get A, it has a 2-page proof that we done. You have this function based on your input scalars. My main aim is to only play with the input scalars to represent the bit streams without the bit streams. For the 0 correlation, if we initiate a value, we have this formula. We just multiply two scalars, divide by n, and we round it to the nearest integer because a is just an integer value or 0. Up to that point, I just show you how to decide the correlation and how to set the CT. But after you set the CT, you need to implement the logic operation. I told you that A is the AND operation because 1, 1 is equal to A, and 1, 1 actually give you the outputs of ones of an AND operation. So if you have calculated the A, you actually calculated the AND result at the output. Here I have the same example again for 4 and 6, and I have some random bit streams. They are uncorrelated, by the way. And I just show you that A, B, C, D here is 3, 1, 3, and 1. You may see that it's uncorrelated because if I multiply 4 and 6, it's 24. If I divide it by n, it's 8, it's 3. So no need rounding to the nearest integer. So 3 as an A value is representing the uncorrelated representation. You may remember from this formula. So this representation is uncorrelated. And after this example, I need to show you, after I decided the CT table, how I can deal with the logic operations. By using the linear combinations of A, B, C, and D, I need to get the numbers of the ones at the output of this logic operation. For example, here we have XNOR, here we have some input bit streams, and I have an output bit stream. What I want to find is total numbers of the ones at the output. So I call it the TCO. In terms of the TCO, I just calculate these ABCDs for each logic operation. It's A for AND, and for instance, it's A plus B plus C for OR. So actually, my main aim is, instead of sourcing the bit streams, I will just source to my circuitry or to my model the scalar values. I will generate A, B, C, and D, and then I will get the output as an output bit stream in terms of total numbers of the ones. So I will have another logic value. Since I am only using the scalar values, there will be another logic operation, but I will have another scalar value. So this logic operation will be having the scalar values only. So I will never generate the bit streams, and I will never process them bit by bit. I will only play with the scalar values. And at the end, I will have the total ones at the output in terms of my CT table. So this was the simulation part. I will be showing you now some conceptual examples of hardware-inspired image processing. You may or may not assume that some examples with or without CT or real actual bit streams. This is not mentioned here in all slides, but in some cases, I will be giving the example of the CT. After the multiplication, I need to present you the addition. There are several examples, several proposals in the literature as an adder, accumulator of stochastic bit streams. Multiplexer is one example. You may remember from your bachelor degree digital circuits course that you have 2 ANDs and 1 OR, and you have 2 inputs. And based on your selection, you just choose first or the second input for the output. And here, for example, for this architecture, I have S not and S for the first and the second input. So I have 3 inputs: first input, second input, and the selection. If you look at the general formula for stochastic output, we have px1 multiplied by 1 minus ps, which means not operation, plus px2 multiplied by ps. This is the general formula for 2-to-1 multiplexer. And if you set your ps value to a probability value, it's 1/2, you will have just addition of the probabilities divided by 2. It's very approximate. It's your total accumulation is divided by 2. This is the reason why it's called a scaled adder in the literature. But however, approximately, we may process our data, especially for image processing applications. When I mention any image processing application, I mean the grayscale values. And each grayscale value is converted to a bit stream, generally unipolar. So you may think that we have a data, 3D data, and XY pixel position, and in the depth is the bit stream. These 2 conceptual examples showing the mean filtering and the edge dejection. These 2 applications having the multiplexers inside. If you cascade some 2-to-1 or 8-to-1 multiplexers, you may have some averaging operation. So your main motivation is to have an output function as an f, which makes add all 9 pixels and divide it by 9. And you make an average operation for 3-to-3 kernel filter that you slide over your image. So if you source your input pixel values to this representation, if you cleverly set your S selection probabilities, like the one example 1/2 in the previous slide, you will have an output function. And this is giving me the py2 is equal to just the averaging of 9 pixels. This is the original image. This is the image with noise. And this is the stochastically processed image, giving the 23 PSNR value. Also, we have the edge dejection. I may just summarize this edge dejection example to you that if you have an excessive noise, since we are dealing with noise-robust emerging computing, we will have this dashed red line at the top. It's just this design with plain design. Compared to all other different color designs like the binary, FPGA, MATLAB, in case of noise, if you just conventionally process your edge dejection, this is actually the gradient calculation. If you have already dealt with an edge dejection, it's just a filter that you decide horizontally or vertically the difference between pixel values that we deal with here. The most important outcome from this example is the noise robustness, that you get the top PSNR values if you just represent your bit streams and process by using this cascaded 3 multiplexer. We have 2 other examples which are actually still under review. One is the template matching, and the other is the bilinear interpolation. Here, I use the maximally correlated bit streams to represent pixel values for my real image and my template. This is a real QR code application. I just try to find the finder pattern as a K kernel sliding over the image. But here, I use a single XOR operation, and I am just maximally correlating them. And for stochastic function from your XOR, if you have maximally correlated bit streams for I and K, you will have absolute subtractor, and it's just not random. It's because it's a maximally correlated. It gives you the perfect absolute subtraction. So we have the accuracy of 100 here if you don't have any noise. Here, that plot actually shows the memory consumption of real bit streams and my CT approach. If you use CT, you may have up to 2K memory enhancement instead of generating and processing the bit streams. Also, we have the bilinear interpolation. It has a function, and 4-to-1 multiplexer function coincides with the function of bilinear interpolation. I will, in next slide, I will give another example for image compositing, and you will understand the details how coincide, what is coinciding is. But here we may just mention about the when we process the actual bit streams and my CT simulation approach, actually we take the account of random fluctuation error in stochastic computing. So based on your different random number generators like LFSR, like Sobol, binomial distribution, you need to take the error into account. So the PSNR values of these 2 applications we have is actually very close PSNR values between each other. After these conceptual examples, I just give you a little larger example to show this what is coincides mean. We have a background and foreground image, and we want to composite these images. This is also a very recent topic in the literature, some neural networks trying to composite 2 images. If you have 2 image, background and foreground, you try to make them together. And the conventional formula, if you just look at any computer vision book like Zylitsky, you will see that formula, B multiplied by 1 minus alpha, F multiplied by alpha. This means that B is the background pixel, F is the foreground pixel, alpha is the opacity value of your foreground pixel. The leftover sides of your background in the foreground is alpha, actually. So you have this formula, but also, if you remember, I have this formula from multiplexer. While I was taking the computer vision course, it was in my mind that this formula and the multiplexer formula coincides with each other. So we have px multiplied by 1 minus ps plus px2 multiplied by ps. So if I somehow set B, alpha, and F for the inputs and the selection port, I may have the multiplexer output function in terms of the image compositing function conventionally represented in the literature. What does this do is just at each pixel value, you represent the bit streams for B, alpha, and F. You source them to your multiplexer with just 3 logic elements. And at the output as a bit stream, you just get your composited image. This is a real example that we do. We have this and the dog image as a foreground. We just combine them by using this multiplexer. And we also imitate the random fluctuation errors. It's just another topic. I will not giving the details today for LFSR, Sobel, and binomial distribution. And our PSNR values for the CT and actual bit stream comparison, what I mean, our Agile simulation approach, we just run with this red and the green actual bit streams and the CTs. If we compare them, they are just following each other. In addition to that approach, we also prove our simulation approach with this table. So now I will giving some machine learning examples under the title of learning machines, because we will be dealing with some hardware. Binarized neural networks, is just from 2015, I guess. It's very famous, and there are different applications and different hardware designed for this. I'm sure all of you know a little about the neural network systems. You have some layers and you have some neurons. Basically, you just multiplied your weights and your neuron outputs or inputs from the first layer, and you just multiply and add them. And then after you multiply and add them, you just use an activation function. In binarized neural networks, there is a restriction. And what they do is represent each weight value and the neuron outputs +1 or -1. And they use the sign function to guarantee each neuron output is either +1 or -1. So you deal with the binary values. They are +1 and -1 as the binary values, but in hardware, we may think that they are 0 and 1 in terms of logical values. And you need a sign function as an activation function. And your outputs are always a +1 or -1 thanks to the sign function. And you train your system to be sure about the weights are +1 or -1. The motivation based on only dealing with the binary values for the multiplication. And if we have +1, we have actually the logic 1. If we have -1, we have actually the logical 0. And if we do just the scalar multiplication, like in software, and if we do the logic operation in binary module, we will be seeing that XNOR operation is equal to the multiplication in terms of the bit processing. So for instance, if you have 1, 1, 0, 0 here, like +1, +1, -1, -1 multiplied, and the result is +1, and your result is logical 1. So conventionally in the literature, they propose to have a lightweight, efficient neural network architecture thanks to this bit representation. Here, I just want to open a parenthesis. The sign function guarantees the outputs of the neurons are +1 or -1. For the weight values, you need to train your neural network by considering your backward pass. So at the forward pass, you multiply, accumulate, and apply your sign function. You always keep the 2 copy of your weight values, the floating point representation and the binarized versions. And when you are calculating the error at the output, you are dealing with the binarized versions. You just binarize them. And on the backward pass, your stochastic gradient descent, you just apply your, at each point, your binarized values. And while you're updating your weights, you update your floating point weights. And in the forward path, you again apply the binarization while you are going the forward path. But at each time you do this, and at each epoch, you just update your weights, but for the floating point weights. But at the final case, when you finally update your weight values, you just finally convert them to the binary values, and you guarantee that your weights are just +1 or -1. For conventional binary neural networks, in addition to this computer science information, let's look at the hardware side. I mentioned you that we have the X as a data and weight data or neuron output value. We need to multiply this XNW with XNORs. This is their proposal. This is the prior art. And after that, we need to pop count these values as just the binary values. So we need to look at how many ones we have. Something very similar to stochastic computing, actually. Here at that point, BNN and stochastic computing neural networks kind of having some common point. And this pop count operation is just a counter, just decides how many ones you have. And then for your neuron output, you have total ones after this multiplication and accumulation. And at each neuron, next neuron, you need to trigger or not by looking at a threshold value if you're greater or not greater than this threshold value. So you need to make a subtraction. The conventional hardware architectures doing so, but what we do propose is by using the stochastic bit stream representation on X and W's throughout the all networks for the X bolt notation and W bolt notations, we again do the XNORs. You may remember that if you are using the bipolar encoding, your multiplier is XNOR. So you represent this X and W with the bipolar encoding, and you apply the XNOR. And after that, you just pop count it. But here, different from the prior art, thanks to the binary bit stream representation, we may decide the neuron trigger while we are doing the population count. Because you may remember that exactly the middle point, 0, is the indication of +1 or -1. So while I am making a pop count, if I somehow decide that I am in the halfway or more, I may decide that I am +1. If I am not at the end of each clock cycle, I may conclude that I am -1 for the neuron output. So I never do any subtraction. So I just cancel the subtraction module. And I always check while I am popping up for my counter, I always check if I am above or not yet above the threshold value that I have. So let me give you an example. I have 3 neuron inputs, ones and -1s, the weight values, because it's a binary neural network, and X values, because this is the input layer. Input layer doesn't have to be binary. For the X, I may have 0.5. I represent these inputs, X and weight values, in terms of the 4 bit size bit streams. I just XNOR them for the multiplication. And after I XNOR them, I obtain the outputs as the multiplications. And after the multiplication, I need to accumulate them. So what I do is, I need to, let's assume that I'm concatenating them. I need to decide what is the large size, maximum size of my concatenation. Here I have 3 inputs, and I have 4 as a bit stream size. 4 multiplied by 3 is equal to 12, is the total size that I have. This is important because half size of it, if with flow of ones, it means that I am at the 0 point in the bipolar representation. So if I somehow understand that, at the next cycle, I may just trigger my neuron and I continue. If I, till the end of this 12th cycle, I decide that it's let's say many zeros, majority of zeros, then I don't trigger and it's a 0 or it's -1 in binary representation. So this is the reason why I somehow truncate my counter by deciding the T threshold value based on the half size of this concatenated multiplications, concatenation of the multiplications. So here, for example, it's 6, including the 0 position, it's actually the 5. And I create a masking logic, and I put this masking logic. If you obtain this value, this 5 at the output of your counter, you will just stop counting and you will go with the next step. Here, for example, for this 3-bit example, I have the flip-flops, and this is the counter example, and I have my masking logic. And at the output of this Q1, Q2, and Q3, they are the binary outputs of your 3-bit counter. If you have half size of your concatenated multiplications or more with flow of ones, then you just decide with your masking logic, and you just stop counting and you trigger your next your neuron output. So here, for instance, including the 0th state, if I obtain the 6th one, which means that 0 or more is equal to +1, I just stop counting and continue with the next step. So I don't do any thresholding operation, and I decided with this simple several gate masking logic. So this is actually based on this bipolar representation, and I have a middle point. I have the half size with ones, which means I just assume that 0 and 1 is equal to +1, -1 is equal to -1. So if I have majority of ones starting from here, decided in here, which means that my neuron output is +1. By that representation, I just use for the stochastic representations 8 or 16 bits. You may ask, our main aim is just to represent the single bits for the weight values, but we increase it to the 8-bit. Compared to the conventional stochastic representation, 8 and 16 is actually not big values. And also, there is another motivation, because the conventional binarized neural networks representing the single bits for your neuron outputs and the weight values, it's error prone. So if you just flip your bits, you may have some problems if you are using some emerging memory environments like ReRAMs, carbon tubes or something. So if you are having some emerging computing memories, you may have some problems in case of the bit flips. So keeping 8 or 16-bit and using the stochastic bit stream gives you two opportunities to have noise robustness and efficient hardware design. We don't have any activation units, as I said. We do accumulation and activation concurrently, and we have 30% better hardware accuracy in terms of the lookup tables and the registers, and we are robust to bit flips. Here, I show an example for MNIST. Conventional BNN accuracy for MNIST is 98.27. It's just the conventional multiplications for the BNN architecture for 8-bit binary representation. And we have BSBNN, by bitstream processing binarized neural network, our proposal. And with 8 and the 16-bit representation, if we have applying some bit flips to our data represented, like MNIST images, like a 2, 5, 10, or 20% of the bit flips throughout your data, you may have the accuracy drops in your conventional design from 93 from 98 to 93 for 5% bit flips with this representation. And even if you increase it, you will have 70% accuracy. But with our proposal, even though you have 10% of bit flips in your data representation, you still, with the 16-bit bitstream processing binarized neural network, you are around 96% of accuracy. This is the weight bit flip example. This is showing us the increased numbers of the bit flips throughout the weight values. We just flipped the bitstream processing BNN and conventional BNN. And starting from the 10% of the bit flips for the weight values, especially the BSBNN, our proposal with the 16-bit is way better than the BNN and the 8-bit BSBNN. So finally, I just proposed an Agile simulation platform for bitstream processing systems. I proposed not to use the bit streams, but to obtain the expected values. And it gives me the runtime and memory advantage. And for image processing, I applied it to template matching, image compositing, and the bilinear interpolation first time. And I also extended the perspectives for mean filtering and edge detection. And finally, I applied this emerging computing methodology to binarized neural networks, showing efficient hardware and bit flip robustness. These are some selected papers from my PhD, and you can download my PhD thesis. And thank you very much for your attendance.